All right. Chapter 6.3 talks about Taylor series as well as Maclaurin series. The Maclaurin series is just a special type of Taylor series. So essentially, our definition in this first bit here. So if f has derivatives of all orders at x equals a, so that means you have to be able to keep taking derivative at, up to n orders or infinite orders, whatever. Then the Taylor series for this function f at a is this. So we have a summation here. We have f to the n. So recall this f to the n of a. This means the nth derivative of f evaluated at a. That's what that means. That's what this notation, this fn, f to the n of a means. That'll be over n factorial and then multiplied by the quantity x minus a to the n power. So what this equals is when we put in the very first value of 0, well, what happens? It's just our function evaluated at 0, or in this case at a, because we're looking at the function at a because we're evaluating it at a. That's our first value. 0 factorial is just 1. Then next we're going to need to take the first derivative of it evaluated at a and then multiply by x minus a to the first power. Then we take the second derivative here. We're over 2 factorial. This other one was over 1 factorial, which is just 1. And then we have x minus a raised to the second power. And then the third derivative evaluated at a over 3 factorial, and then x minus a to the third power all the way to this nth derivative over n factorial and x minus a to the n. Again, the nth derivative evaluated at a. We evaluate f at 0 for Maclaurin series. So that means just instead of using a, we're using 0. So it's just a very specific and generally an easier type of Taylor series to do. The next theorem is uniqueness of the Taylor theorem. If a function f has a power series at a that converges to f on some open interval containing a, then the power series is a Taylor series for f at a. So there's just one of those essentially. And then we have a final definition here, which is kind of restating what we're doing. So if f has n derivatives at x equals a, so not infinite amount, not all orders, but just n of them, then the nth Taylor polynomial for f at a is below. And this should look a lot like what you have above. So these two definitions are very similar. I'm going to try to do an example here, and I'll use sine of x, and I'm choosing a Maclaurin, which means that a equals 0. So f at 0 is equal to sine at 0, which is just 0. F prime at 0 is equal, the derivative of sine is cosine. And cosine at 0 is 1. Second derivative of cosine is negative sine. So we're looking at negative sine of 0. So that's still 0. Third derivative of negative sine is negative cosine. So that gives us negative 1 there. And then everything repeats. I'll do the f to the fourth. That's just back to sine again. So we're going to have this sort of pattern. It'll go 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so forth. So I'm going to start writing down over here. So essentially, the series, so this And we'll write the first one is PO at x is just 0. All right, with sine of 0 is 0, it's just going to cancel out. We're just looking at f of a there. It's 0. So our next one, P1. So we have that 0, and then we have to take the first derivative, which is that 1 over 1 factorial. And then it's x minus 0, so it's just times x. Our second one, I guess P2, which would be our third one. That's another 0. In the third spot there. So 0, 1 over 1 factorial x plus 0. Now we have a plus 1 over, so that's 2 factorial, so this would be 3 factorial. And then we take negative 1, and then we have our x to the third power. And let's do a couple more. Let's do P4 here. And I can clean up some of what we have. So 0 plus, this is just x. I don't need to have the 1 over 1 factorial. That was just for demonstration purposes. And then this next one is going to be negative x cubed over 3 factorial, which is 6, and then another 0. So ultimately, if we follow this pattern, Pn at x is our first value. We don't need the 0. We're going to have an x, right? Then there's another 0, and then we go to this negative x cubed over 3 factorial. And then the next one will be positive x to the 5th over 5 factorial. And the next one will be a negative, x to the 7th over 7 factorial. And then the next one will be positive x to the 9th over 9 factorial, until eventually we get to a negative 1 to the n, and then it's x to the 2n plus 1 all over quantity 2n plus 1 factorial. So this is what we're going to have for sine. And so because we have this equals the sum of n equals 0, or x, well, we're going to n, excuse me. So let's pick a new letter. K equals 0 to say n. And then we have that negative 1 to the k. And then we have our x to the 2k plus 1, all of it. Don't do 2k and then, like, you don't distribute that. And that's all over 2k plus 1 factorial. And that's a representation of sine, and that's how you can find the nth Taylor series point.